A series circuit is a circuit in which two or more elements are connected end to end so that a single loop of current is formed. The equivalent resistance is just adding up all of the resistance. So R total equals R1 plus R2 plus however many resistors there are. The current is the same throughout, so it'll obey Ohm's law, and the total current will be the total voltage over the total resistance. The voltage, much like the resistance, will just add up. So however many voltages there are, V1 plus V2, and so on until you have them all. All the components must obey Ohm's law. Let's try an example. Here we have a 7.5 volt battery. It is connected in series in a single loop with 3 resistors, and there is also a switch. The 3 resistors can be added up for a total resistance of 15 ohms. We can find the current by setting the current equal to the total voltage over the total resistance. That's 7.5 volts over our newly found 15 ohms. And that'll give us half of an amp. We also mentioned before that your current is going to be the same throughout the circuit, so everywhere it will be 0.5. Now that we have the current and resistance for all 3 of our resistor, we can use Ohm's law, rearranged and solved for voltage, to solve for the individual voltage drops over each resistor. Over resistor 1, voltage drops 2.5 volts. Over resistor 2, voltage drops 4 volts. You can either subtract the 4 and the 2.5 from the total voltage of 7.5, or you can do out the drop over the 3rd resistor. Either way, the math will work out and give you the final volt dropped over resistor 3. We can also show this series circuit as if all of the resistors were a single resistor, in which case they would be a single 15 ohm resistor in series with a 7.5 volt battery. Example 2. Here we have another series circuit and some information given. Here we are given an ammeter that is showing 1.5 amps. I am also showing the direction in which current flows, as I always do. So they gave us the current, and we do know that it's going to be the same everywhere, and it's going to be 1.5 amps. You can see that I mistakenly thought I saw 2.5. I'm correcting that now. It is 1.5 everywhere, as indicated in the ammeter. We can add up all of our resistors and get a total of 320 ohms. And now that we have our total current and our total resistance, it is a simple use of Ohm's law, solved for voltage. We fill in our totals, and we will get a total voltage of 480 volts. That's going to be the value on the battery. We also have the current and the resistance for all 3 of the resistors, and so we can use V equals IR over the first resistor with the first resistor's value to find 75 volts dropped over the first resistor. The second resistor, V equals IR, will equal 180 volts. And then again, if you use Ohm's law, or if you subtract all of the voltages from the total, you will in both cases get 225 volts. That's the voltage drop over the 150 ohm resistor. Again, I like to show you that all of the resistors can kind of be thought of as a single resistor, in which case they would just be the total resistance, a 320 ohm resistor, and that circuit would behave the same. Let's practice. The battery in the circuit below supplies it with a potential difference of 160 volts. This battery is put in so that the positive terminal is on the right-hand side, and the current is flowing counterclockwise. We do know all of our resistor values, so we can fill those in and add them up. We'll then be able to solve for our total current because we will have both our voltage and our total resistance. So we'll put those into Ohm's law, 160 volts over the 80 ohm total, and that'll give us 2 amps for the current. It's a series circuit, so the current is the same everywhere. Once we do that, we have the current and we have the resistance for each resistor. So we put those into Ohm's law to solve for each individual voltage drop over each of the resistors. Here we see for V3, it's going to equal the current 2 times the value of the resistor, which is 50, and that'll be 100. We also need to put an ammeter in this circuit so that it measures the current going through resistor 2. I'm going to put it in front of resistor 2. You could also put it directly behind resistor 2. And we also need to put a voltmeter in so that it reads 100 volts, and that is resistor 3. Resistor 3 has a voltage drop of 100 volts, so if we put a voltmeter in parallel with resistor 3, it will read that 100 volt potential difference. Let's draw a circuit with all of the elements required for number 2. We need 2 resistors, a 12-volt battery, a switch, an ammeter, and a voltmeter that's going to measure the potential difference of the battery. Experience will show you that usually we try and make rectangular shapes. If we can, we give each component or element its own side, or otherwise try and evenly space it out so we can clearly look at circuit diagrams and point out all of the parts and components. You might put your resistors in a different order than I did, or you might even put the battery on the top side. It doesn't really matter as long as it is obeying the laws of physics, but usually we put the battery at the bottom. I'm sure someone will fight me on that, but I think it's proper etiquette. And I'm just labeling my resistors before I finish. Number 3. Let's do this circuit chart. We do have a total resistance and 2 of the 3 pieces, so we'll subtract them away from the total to get the remaining resistor, which is 80. Now we have a voltage and a resistance for resistor 1, so that we can use Ohm's law to solve for the current. We'll get 7/2 of an amp. We'll recall that series circuits will always have the same amperage everywhere, so that's 7/2 everywhere. And now we can basically use any row that we would like to solve for the voltage. For the total voltage, we'll be using 7/2 and 150. For the voltage across each of the resistors, it'll be I times the value of that resistor. And the remaining pieces will be 35 volts and 210 volts. Now we're going to sketch the circuit. And again, I always commonly start with my battery at the bottom, and then I usually move around in a clockwise manner, trying to put only a single resistor in at a time, or a single component in at a time, and labeling them. So here, resistor 1, 2, and 3, I'm just labeling in a clockwise manner. You might put them in a different order. That's totally allowed. Let's do parallel circuits. So first of all, this section, look, it says a series circuit is a circuit in which two or more elements are connected so that each has its own current loop. Obviously, this was incorrectly printed because this is the section on parallel circuits. This is a parallel circuit. The equivalent resistance, more resistors, is less resistance, and it obeys this equation. We add up all the resistors again, but this time it is 1 over each of the resistors. The current in each branch adds together to be the total current. And the voltage going into each branch of a parallel circuit is equal. So voltage going into branch 1 equals branch 2, etc. And we have to obey Ohm's law. The junction rule. This is what a junction looks like. So I have to choose a direction in which my current is going. If 10 amps is going in, it separates into 4 amps and question mark or 6 amps. Here, I have 10 amps going this way towards a junction where it splits into 2 and here it'll be 8. Here's another junction. 8 splits into 6 and 2. For example 1, the current is going to be the total current until it gets to the first junction. At that point, it'll split. You'll have I1, I2, and I3 going over R1, R2, and R3. When the junctions come back together, it'll be I total again through the battery until the junction splits it again. The equivalent resistance will be 1 over R total equals all of these added together, which will be 1/10. I'm going to flip both sides of this equation to just get our equivalent resistance, which is 10 ohms. Now I can get the total current because I have the total voltage and the total resistance, and that'll be 6 amps. But remember, for a parallel circuit, it is the voltage that'll be the same everywhere. The current is going to split. So I1 will be voltage over R1, or 2 amps. I2 will be voltage over R2, or 2 amps. And in fact, all three of them are the same value. It splits evenly. Here we have our current, the total, until this first branch. It'll split into I1, I2, I3, which is marked here on an ammeter, so we know that that is 0.5 amps. We're going to start with finding our total resistance again by using the equation to add them up. Again, I do like to utilize the flipping both sides of the equation, and that'll give our total 5.88 ohms. Once I have I3 and R3, I can find my voltage using Ohm's law and solving for V. And I'll recall that the voltage will be the same everywhere. And now that I have my voltage and my resistance for each of my resistors, I can use Ohm's law solved for current to find each of the currents across the resistors branches. Here we're going to get 0.25 amps, 0.1 amp, and 0.5 amps that are going to add up to 0.85 amps. The battery in the circuit below supplies it with a potential difference of 160 volts. I do know that 160 volts is going to be the voltage everywhere, and here is where the junction happens and splits into the 3 currents, or the 3 branches there, and it comes back together at this junction to the total current. I have the values given for my resistances, so I'm going to fill them in. I'm going to use my formula to find the total resistance. When I add them up, I'm going to get one expression equals another expression, and I'm allowed to flip both of those. interchange the numerator and denominator, and that's how I am solving for the total resistance. Once I have my voltage and my resistance, I can solve for all of the different currents that I need. I need total current, so I'll put total over total. I need I1 and I2 and I3, so I'll put my voltage over R1, R2, and R3 individually and fill in those pieces, and I can confirm that I can add up all of my individual currents and it should equal my total current. Otherwise, something has gone awry. What else do we need to do here? All right, we're going to put an ammeter that's going to show the current for R1, and that'll happen either before or after the resistor is just fine. And then we need to measure the voltage drop across the battery. Here we see in this junction 5 amps going in, 2 amps going away. We're missing 3 amps going away. In this junction, 8 and 5 amps go in, so 13 amps must be leaving. In this junction, a total of 16 amps is shown going into the junction, and out there is a total of 21 amps when you add those all up. So what's missing? Well, there is a missing 5 amps going in, so that a total of 21 amps can get out. Our last question is just going to be showing a parallel circuit. You should try and separate your components as much as possible and, of course, label.